It's a pleasure to introduce Agustina Czenky from the University of Oregon. She will talk about another dimensional modular tensor categories. Thank you, Agustina.
Thank you, Moniki, for the introduction, and thank you also to the rest of the organizers for inviting me to give this talk. I'm going to be talking about joint work with Julia Plapnik, who is also here from Indiana University. Okay, so first I will give a couple of definitions and results that will be useful for us in our context. Then I will be talking a little bit about um, our motivation. So what was the question that we wanted to answer? And then I will show you some of our results. So first, what we do is we prove some relations between the ranks of the different components of a faithful grading of an odd-dimensional modular tensor category. And then we apply these results to classify maximally non-self-dual modular tensor categories of low rank. And by this, we give a partial answer to the question that we have. And then I am going to tell you a little bit about what we'd like to think moving forward. Okay, so in this talk, I will always be working on an algebraically closed field of characteristics 0. And I want to give you the definition of modular tensor category. So let's start with the definition of a fusion category. So for us, a fusion category is going to be a tensor category that is both finite and semi-simple. So by finite, I mean that all home spaces are finite dimensional. We have enough projectives, and we also have a finite number of simple objects. And by semi-simple, we know that we can write every element in our object as a sum of the simple objects in the category. And when I say rank of the category, what I mean is how many simple objects I have in the category. So that's something that we're going to be using quite a lot, because what we wanted was to work with low rank modular tensor categories. So modular categories that have a small number of simple objects. Okay, now our fusion category is going to be braided if it can be equipped with a braid, which is a natural isomorphism from X tensor Y to Y tensor X for every pair of objects X, Y in the category. So this is what we call the braid. And we ask for this isomorphism to satisfy certain commutative diagrams that, well, they have to do with the different ways of associating the tensor product in the category. And we say that our category is driven if it has a braid and it also comes with another natural isomorphism. In this case, it's going to go from X to X, and we will call this twist. And we ask for this isomorphism to satisfy two relations. So the first one is the twist of the tensor product is the tensor product of the twists. And we compose that with the double of the braiding. And we also ask for a condition that has to do with duals in the category. Okay, and now finally we can define what a modular tensor category is. So we will ask that our category comes with a twist and with a braid. And when we have this, we are able to define a notion of trace in our category. And so we can consider the S matrix of the category, which is a matrix that is indexed by the simple objects in the category. And in each entry, we have the trace of the double of the braiding. And what we're going to ask is for this matrix to be invertible. So when that is the case, we say that we have a modular tensor category. Okay. So some more definitions. We will say that an object in our category is invertible if both the evaluation and co-evaluation morphisms are isomorphisms, or equivalently, that the Frobenius-Perron dimension of the object is 1. The invertible objects in the category form a group with a tensor product that we call the group of invertible objects. And we can also look at the fusion subcategory generated by the invertible objects, and that's what we will call the pointed subcategory. Now, we will say that the category is pointed if it's equal to its pointed subcategory. So all simple objects are invertible. And in that case, it is known that the category is equivalent to the category of G-graded vector spaces, where G is a finite group and omega is a 3 co-cycle. So on the other end of the spectrum from pointed, we have the notion of perfect. So we say that the category is perfect if the only invertible object is the unit. So pointed, all the simple objects are invertible, and perfect, only the unit is invertible. Then we will also need maximally non-self-dual. So we say that the category is maximally non-self-dual if the only self-dual simple is the unit. And the last definition is that we say that the category is integral if all objects have Frobenius-Perron dimension and integer. Good. So now we have all of these definitions that we're going to be using all the time. And I have here a compilation of results from N. Schauenberg, Hong, Rowell, and Helaki Nikschik that combines some of these. So when we're working with a modular tensor category, having odd dimensional Frobenius-Perron dimension is equivalent to the category being maximally non-self-dual. And another thing that we have is that if the Frobenius-Perron dimension is odd, then the category is integral. So when I am talking about maximally non-self-dual modular tensor category, you can think about it as a modular category that has all Frobenius-Perron dimension, and all of the simple objects have integral Frobenius-Perron dimension as well. One thing to notice is that when we are working with a maximally non-self-dual modular category, then all of the rank of the category is going to be an odd number. So maximally non-self-dual implies odd rank. Okay. So let me tell you a little bit about our motivation for our work. So in a work by Brilliard and Rowell, they show that maximally non-self-dual modular categories of rank up to 11 are all pointed. And they also found an example of a non-pointed maximally non-self-dual modular category of rank 25, which is the category of representations of the double of this semi-direct product. So all the way up to 11, they could show that these are all pointed. And the first example that they found was at rank 25. So a natural follow-up question from this is what happens between 11 and 25? So is it also true that maximally non-self-dual modular categories of rank less than 25 are pointed? So the first non-pointed example appears at 25. So that was our question, and we were able to give a partial answer to this question. So we worked with modular categories from ranks 13 to 23. Remember that when we are working with a maximally non-self-dual modular category, we have that the rank is an odd number, and we proved some relations for the ranks of the category, and that's how we obtained our results. So let me tell you a little bit about what we know about the ranks, bounds on ranks. So whenever we have a fusion category, we can consider its universal grading, which is a way of decomposing the category into a sum of components. And here the grading is given by what we call the universal group. And this universal grading is faithful, which means that all the components are non-zero. And in particular, the trivial components, so the component that corresponds to the identity element, is the adjoint subcategory. So that's the subcategory generated by the tensors X tensor X dual for X, an object in the category. And in particular, when we're working with a modular category, this group that indexes the grading here, so the universal group, is isomorphic to the group of invertible objects. So that was something that we used a lot for our results. Okay, so our first result was for any odd prime that divides the number of invertible objects in the adjoint subcategory, there must exist some component in the grading that has at least p non-invertible simple objects of the same dimension. So if for any prime that divides how many invertible objects I have in the trivial component of the grading, I know there must exist another component that has a certain a certain amount of simple objects. And we also get that when C is not pointed, then there is a lower bound for the rank of C that has to do with the rank of the adjoint subcategory, the pointed subcategory, and that prime. So this was very useful to us because we were working with low rank modular categories. So this number we knew was small, and that left us with not that many options for how many invertible objects the category could have. Okay, another thing that we proved and used is that if C is odd dimensional, then the number of simple objects in every component is equivalent mod 8. So if I know how many simple objects I have in one of the components, I can say something about how many I have in the other components as well. Okay, a couple more results. So if the adjoint subcategory is perfect, so remember that means that the only invertible object is the unit, then the rank of the category is the product of the ranks of the adjoint and pointed subcategories. So in particular, if our category is of prime rank, then it can either be pointed or perfect. So this was also useful to us because in some of the ranks that we were interested about from 13 to 23 were prime. So yeah, we could get something out of this. And also we have that, well, for a very specific setting, so what we need is that the category is non-pointed, that all invertible objects are inside the adjoint subcategory, and that the Frobenius Perron dimension of the pointed subcategory is power of a prime, an odd prime. Then for all the components, except perhaps the trivial one, that prime must divide how many simple objects we have in the component. And moreover, it divides how many simple objects we have in the component for a fixed dimension. So again, in this particular setting, we can say quite a few things about how many elements we have in the components of the universal grading. And this actually happens a lot for our low rank categories. Okay. So now let's look at the categories that we wanted to work with. So that's modular, tensor categories, maximally non-self-dual. The rank is between 13 and 23. So when we have a category of this type, then if we assume that the category is not pointed, it happens that the adjoint subcategory is perfect if and only if the category is perfect. And so with this result and all of the bounds on ranks and the relations between the ranks that we just talked about, we were able to discard a lot of possibilities for how many invertible objects the category had. So that was very straightforward from all of what I just talked about. So if the category is not pointed, because we wanted to prove that they had to be pointed, so if we assume that it's not, then for rank 13, the only possibilities that we have left are that we have 1 or 3 invertible objects. And for the rest, so from 15 to 23, we have 4 options, 1, 3, 5, and 9. So what we wanted to do was discard these cases now, and we were able to do it for some of them. So our main result here is that maximally non-self-dual modular categories of ranks 13 and 15 are pointed. So this extends the result by Brullier and Rowell. They had done it up to 11, and so we can add 13 and 15 to that. And so the way we did this is we had to discard 1 and 3, and then all these 4 for, well, 1 and 3 for 13, and these 4 for 15. And the cases when it's greater than 1, so 3 for 13 and 3, 5, 9 for 15, those also were kind of straightforward from all of the results that I previously showed. We had to do a little bit more computations, but we could still use those to discard those cases. And so the problem cases were when we only have one invertible object. And for that case, we had to do something different. We had to look at the dimension of the modular category, and we know that we can write that as the sum of the squares of the dimensions of the simple objects. And well, we have kind of small sum because we don't have that many simple objects. And we know that for these categories, the square of the dimension of the simple objects divides the dimension of the category. So that was also something that we used a lot. And so we were able to work with all of these dimensions, looking at the possibilities for them. And in the end, we arrived at the contradiction that it wasn't possible. And so we were able to discard the case where we only have one invertible object for 13 and 15. But for the other cases, so from 17 to 23, that computation got a little bit more complicated. So for those cases, we can only conclude that the category will either be pointed or perfect. So we have that it's pointed, although the only invertible object is 1 because we couldn't discard this case here. Since we have more simple objects, the computation gets a little bit more complicated with many cases. And okay, so those are our main results. And I want to tell you a little bit about what we think will happen. So there is a version of the Phi-Thompson theorem for weakly group theoretical fusion categories. So this is a result by Natalia and Plavnik that says that odd-dimensional weakly group theoretical fusion categories are solvable. And then we have another result by Ettinghoff, Nikschik, Ostrich that says that non-trivial solvable fusion categories contain non-trivial invertible objects. So from these two things, we can conclude that a non-pointed maximally non-subdual modular category of ranks between 17 and 23 cannot be weakly group theoretical, because we just said that if it's not pointed, then it's perfect. And they are all odd dimensional, right? So a category like this, if we were able to find such a category, then it would be a counterexample to a conjecture that says that weakly integral fusion categories are weakly group theoretical, because these categories are integral, in particular weakly integral. So we think that that's not going to be possible, that in the end they will have to turn out to be pointed because of this. And in fact, if we were able to find any example of a perfect odd dimensional modular category, then that would be a counterexample to this conjecture. So what we think is that what happens is that odd dimensional modular categories cannot be perfect. So they have to have at least one non-trivial invertible object. And yeah, that's what we would like to think about. Okay, that's it. Thank you.